Hello everyone. Now, some more basic typical problems you will see determining the residues of values. So, determine the residue of each of the following within their given modulus. So, 71 mod 3. What this is just asking for really is like what is you'll see this written like this commonly. What is 7 mod 3? 71 mod 3. And the simplest way is the residue, just think of the remainder. We do 3 divided with 71. 3 goes into, I'm going to write that a little higher actually. Let me just write it up here. 3 divided with 71 goes into 7 twice. 6 minus, I'm going to 1, drop the other one. 3 goes into 11 3 times for 9. And we get 2 as our remainder. So 71 is equal to 71. 71 mod 3 is the same as 2. Now, sometimes you'll see just the answer written as a 2. It's always under the implication that we're under 2 mod, whatever that system was, so mod 3. You may also see like 71 is equal to 2 mod 3. It's all the same thing. It's just some books, some authors, some mathematicians write them in different ways. Mostly to save some time in writing. But as long as we write that mod 3 even once, the assumption is it's always going to be under mod 3. Alright, so part B. Negative 14 mod 8. Now, with the negative numbers, you can do the division, but then you have to remember to go in reverse in the cycle, like we did on that one problem where we had to find a negative congruence. So sometimes for these problems, I like to do them in the following way. Just use division algorithm. Negative 14 is the same as 8 times what number plus our residue? Well, if I do negative 2, that's going to be negative 16. And if I add 2 to negative 16, I get negative 14. So my remainder would be 2. So it's congruent to also 2 under mod 8. And, to be a completionist, just to demonstrate, we could do the division where we do 8 divided with 14, goes in once, 8, subtract it with each other, we would get a 6, but under the modulo 8 system, our values would be 1 or 0, 1, 2, 3, 4, 5, 6, 7. If it was a positive 14, sure, we would go 1, 2, 3, 4, 5, 6. But since we want to find for negative 14, we would have to go back 6. 1, 2, 3, 4, 5, 6, and arrive at positive 2, just like we did using the division algorithm. So that's why I think in some cases, especially with negatives, the division algorithm is a bit easier. Now, 14 mod 8, well, I just kind of erased the word for that. It would be 6. Because your remainder when dividing is 6. So, 6 mod 8. Okay, 194 mod 11. So I'm going to divide 11 with 194. It goes into 19 once. So we have 11. 19 minus 11, giving us 8. Drop the 4. It would go into 84 7 times for 77. And now we have, that would be 84. 7 and 14. 84 minus 77 would be 7, with the remainder of 7. So 194 mod 11, we get 7. Then 3,944 mod 9. So we can just do 9 divide. Well, if I'm going to do long division, let's just use where we have some room. So 9 divided with 3,944. 9 goes into 39 4 times for 36. Subtract, you get a 3 and a 4. Then it would go into 34 twice. No, what? 3 times. For 27. And yikes, this is gonna be ugly. All right. So that would be 14 minus 7 for another 7. And drop, we would pretend like we were dropping the 4. How many times does 9 go into 74? 8 times for 72. And we get a remainder of 2. So 3,944 is the same as 2. Then finally we have 21 mod 21 for 471. So 21 divided with 471. 21 would go in twice, and 2 times 21 being 42, which would get us 5. Drop the 1. 21 going into 51 twice again. So we would get again 42 and 9 as our remainder. So 471 mod 21 is the same as 9. So those are just some examples of basic modular arithmetic problems where we have to find the residue.